Hey everyone, so in this video we're going to be looking at review problem number 7 for unit 3, and it essentially is a small mass that is just spinning in a circle. That's really kind of the gist of it, but instead of hanging a mass down here, instead to kind of counter and keep tension in the string so the ball or mass, whatever this thing is, stays in a circle. It's a spring scale, so you can spin it faster or slower, and essentially you can read right here whatever the force is in the string or the spring, that then is the same as the force experienced through the string to the spinning object. And so looking at the question here, there's some students, they're studying circular motion, they have this device, and there's a polished glass tube that serves as a guide for the cord. And it says that there's a ball, its mass is 0.2 kilograms. They already converted it. If it was in grams, we have to put it in kilograms because that's kind of our standard unit. And it's attached to the end. They swing it around at a constant speed. That should have been highlighted. So it's at a constant speed in a horizontal circle. So it's not going vertical up and down, like swinging the bucket of water over my head or anything like that. And we're given that the radius is 0.5 meters, so half a meter, which is pretty significant but not huge. And we're ignoring any friction, so the string spinning along the edge of the glass tube here, we're ignoring that friction. We're ignoring any air resistance as this ball kind of whirls through the air. And part A is asking, explain how the students using a timer and all this information up here can find the speed of the ball. Well, really, this hopefully kind of boils down to the idea that speed is really like the distance or change in distance over this change in time. And so that's why they included the timer here for us. That's going to be kind of very crucial or paramount here. But the idea is, well, we know the radius, so we can multiply that radius by 2 and by pi, and then that tells us how far the circle is. We could use the timer to measure for 1 revolution around. I would argue measuring for 10 or 20 revolutions around, and then taking that time and dividing it by 10 or by 20 to get a more accurate measure on it, because you clicking the start and the stop, there's going to be a little error there. But if you time it for 10 revolutions and then you divide by 10, you're also dividing your error by 10. So really for part A, the students can use the timer to find the period for 1 revolution. They may time for 10 or more revolutions and divide, because that would reduce our errors. But otherwise, with the period and the known radius, students would use this equation here. And then they just have to keep in mind that distance really is 2 pi r. And the change in time is the period here. And so that really is it. Now part B here, I have this red X over it, and it's because this actually is a question that's related to our next unit, which is energy. But it's actually a pretty straightforward kind of question. I gave a hint here because I know that this is not something we've gone over. It's saying how much work is done in 1 revolution. Well, it's force times displacement. So we have to go, okay, well, what the heck's the force? Well, if we look at the second portion here where it just says displacement is how far something has traveled. And so in 1 revolution, well, the ball has started right here, and it's gone around and it's ended back where it started. So keeping that in mind, the displacement for 1 revolution is actually 0. So it doesn't matter what the force is, there's going to be 0 work done. And so this was kind of a trick question, just kind of teaching a new concept that you have to find the displacement for something. So if you run a lap around your house, you could be exhausted, but you've actually done 0 work, because if you start and end at the same spot, your displacement is 0. If you looked at like halfway there, it would be different, because halfway there is some displacement, whether it's you around the house or this problem. Now, when it comes to part C, the speed of the ball is 3.7 meters per second, assuming the cord is horizontal as it swings. Calculate the expected tension. Okay, so in this case, we have to look back here and go, well, the tension is going towards the center at all times, no matter where the ball is. So tension is our centripetal force. And this problem is asking us to calculate the tension. So if the tension is providing the centripetal force, we can rewrite the centripetal force as the mass times the speed squared over the radius. We were given the radius. We were just told the speed is 3.7. We know the mass. So that's actually should be a fairly straightforward calculation for this. And so going and plugging in directly, I got 5.5 newtons, remembering that we have to square our speed in this equation. Now, when it gets down to it, it starts getting a little more weird. This is more like a lab a little bit. The actual tension was measured to be 5.8. It's bigger than what I calculated or what I kind of determined. So what's the percent difference? This is actually a throwback to Unit 1, where we had to look at kind of these equations where we have kind of our absolute error. This is the raw kind of amount that we're off. The relative error is really making it into a percentage. That's what it really is. Relative error is the percentage error, and we kind of have the same thing with deviations. So essentially we had to find the kind of raw difference that they're off, and in our case we had 5.5 and 5.8, so that's 0.3 newtons, and then we have to take that raw amount that we're off and then divide that by kind of the correct value. So looking at actually doing that, kind of using that equation, we had to find our absolute error, so kind of the raw amount that we're off. It's 0.3 because 0.5 or 5.8 and 5.5 combined gives us this 0.3, and then the absolute or the relative error is then taking whatever we got here and kind of funneling it into this equation here, knowing that the actual tension, kind of the accepted value, whatever we actually get, is our accepted value. And so we end up getting that there's a 5.2% difference. And maybe you weren't a fan of doing it this way, you didn't think to do it that way. You could have just taken the ratio of them and then times it by 100. So the 5.5 newtons we expected, the 5.8 that we actually got, times it by 100, and you find that, oh, that's 94.8%. 5.5 is 94.8% of 5.8. And then if you go, oh, well, what's the difference between that? Well, that out of 100 gives us the same 5.2, really. So there is actually kind of a second way that's maybe just a little more commonsensical about it. Now, when it comes to part E, students find that no matter how hard they try, they cannot swing the ball so the cord remains exactly horizontal. What that really means is they're not swinging it so that it makes like this perfect right angle, and this isn't going to be a perfect right angle, between, if you were looking at them, this is like where they're holding it right here, and then this is where the actual ball is like rotating. And then if you were just looking at it perfectly flat on, it would just look like this. You wouldn't really see the loop. It looks like it would just be going kind of left and right and left and right. When really, if you looked from above, it would be like a perfect circle. So these are kind of our two profiles. And in part E, they're saying that it does not look like this. They're saying that the student's swinging it, and it's almost horizontal, but it dips down a little bit. So we wish that it could be perfectly flat out across, but there's this little bit of an angle theta right here. And so it says here, on the picture of the ball above, draw vectors to represent the forces acting on the ball and identify the force that each vector represents. Well, it's pretty easy when it comes down to it. The only real forces we have here are tension and gravity on the ball. And it's actually because of gravity that you can't swing this in a perfectly horizontal circle. It's essentially going to droop a little bit. So instead of being like, here's the rod that I'm holding, and having like this kind of perfect oval here, maybe we can even draw more of a perfect oval here. Instead of having something really nice and beautiful like this, we're having something where here's kind of the rod, and then we're kind of having the string droop down a little bit, and then we're making this oval around. And so the string is essentially, it's not perfectly flat, it's kind of drooping downwards a little bit as it swings. It's kind of almost like a, what am I trying to picture here? It's kind of coming down like this, and then it's going in a circle. And so it's kind of like this weird little cone shape of sorts that it really has. And so for part E, we just had to draw the picture. For part F, explain why it's not possible to swing it so the cord is exactly horizontal. Well, that's kind of what we were just saying because of gravity. gravity is always pulling down on the ball as it swings. So this results in kind of this cone shape forming. Now, if you took this out into space and started swinging it, and you were like really far from any planets or anything, you would get almost an exactly horizontal circle. But we can't really do that here on Earth. Now in G it says, find the angle that the spinning segment of the cord makes with the horizontal. So it's essentially saying, like, it's drooping down. Find the angle that the spinning cord makes with the horizontal. And I've drawn it a different way here, and that's totally fine. We could have looked at it as from the perspective of kind of the rod, and then the cord isn't horizontal like this. It's not actually going out horizontal here. It's actually kind of drooping down a little bit. Let's make it solid here. It's actually kind of drooping out, and I've kind of exaggerated it here. We could have said that this is the angle. Instead, I chose to look at the ball itself. That's what I have right here. And I kind of have my tension line going up. So these pictures actually tell the same story. And I've actually gone and kind of drawn my little horizontal here, and I'm saying this angle. But luckily, these actually are alternate interior angles. And so they are, in fact, the same exact angle, theta. It doesn't matter which way you look at it. This is just the way that made the most sense to me in the beginning. But I would imagine that for a lot of people, this is probably the way that makes the most sense for them. And that's totally fine. All we have to do, though, is if we want to calculate the angle, well, we have to know that there is some force tension. And that tension now, looking at kind of my version, my tension here is going to have, let's use blue and green. My tension, I have kind of a y component of tension, and I have, in fact, an x component of tension. And so looking right here, kind of at my picture, well, going straight across here, that would give me the opposite. So here's my angle, and opposite my angle is the y component. So sine would be the y component over the total tension. And similarly, cosine would give us the x component over the total tension. I could then multiply force tension over here, and I could do the same thing over here. And that's exactly how I ended up getting these two equations here. And kind of really, that's a big step that I'm hoping we're kind of comfortable with, looking at something, making the triangle, knowing which one to use for which side, what sine corresponds to, what cosine corresponds to, so that really we can kind of get this alone. And so now we want to find the angle that the spinning segment is making with the horizontal, though. And so I've just gone through and just kind of chased in this direction of all this trigonometry, thinking that this will be useful, thinking that this will be helpful. And now we're kind of going to look at the next step and go, well, the ball's spinning in a circle. It's not going up and down. It's just staying at that same height and orbiting. And so that tells me that the y forces must balance each other out. So more specifically, I'm looking at this and kind of thinking that, well, gravity here must be the same size in the opposite direction as the y part of tension. Those two must balance each other out. If the tension was greater, the ball would actually move up. If gravity was greater, the ball would move down. But we're not having that. Even though it's a little bit of a cone shape, the ball is rotating and going around in a circle, and it's at the same y kind of vertical height. And so what I can do then is I set tension and gravity equal to each other. Those must balance out with each other, and so I just wrote exactly this. And lo and behold, I've already had to use this that I got from our triangle over here. I already kind of had to use this version for the y component of tension. So that was a really wise maneuver, going, hey, there's a triangle here, and just choosing to figure that out right off the bat. Now, there is nothing kind of combating with our x component of tension, and that's good, because the ball's going in a circle, and this x component of tension, even though right here in this moment it's in the x direction, and it looks like it's the same, it's actually always pointing towards the center. And the center is always in the same spot, but it's not always, this is kind of moving, so to speak. If we really kind of think of looking at our ball as it's kind of orbiting from above, if we're looking at it here, well, this y or this x component of tension is pointing here at this moment, and then it's pointing here at this moment. And so in a way, it's always changing, but in a way it's not. So you could say, oh, well, sometimes it's pointing up and to the right, and sometimes it's down and to the left, but really it's pointing towards the center the entire time. And so the ball is having to accelerate. And so what that really means here is that our x tension is equal to the centripetal force, which is really nice. And so what I can go ahead and do here then is say that, well, centripetal force, we know this equation, is equal to the x tension. So again, going and dealing with this triangle really early on right off the bat was a wise move for us, so that we can actually kind of start dealing with these and substituting things in. Now, when it comes down to it all, why have we done all this? Why have we done all this work? What is this driving towards? Well, we have an equation that relates to sine of the angle. We have an equation that relates to cosine of the angle. The entire part G here is saying, what is that angle? And so now what we can do is solve this equation number one. I like to circle and kind of number the equations that I think might be useful. I've circled this, I've called it number one. I can solve this and get tension alone. And then once I have a new version that kind of has this with tension alone, I can plug it in for tension here. And now I will have everything kind of in a nice convenient way so that I know the velocity, I know the radius, I know the mass, and we can just go ahead and get the angle itself is what we're really going to do here. So me getting number one solved for just tension, I get this. I really just had to divide by this sine of theta. So that means I can rewrite this number two here. I can rewrite it as this. I've just rewritten it. All I've done is I've plugged in for this force tension, which is this big kind of nasty thing here. We can see that I have an m and a g and a sine of theta. Now, we're trying to get the angle though. So what the heck can we do? Well, in my opinion, and this kind of depends a little bit on your strength with trigonometry here, we have a couple options. You could go ahead, you could use some trigonometry identities and maybe simplify things down. You could use a cotangent. I just like dealing with sine and cosine and tangent. I want to use as little trigonometry as I possibly can. And so what I've done here then in this equation is essentially I flip-flopped what's on which side. And so if I were to write it kind of in more steps, showing maybe a little bit more work, I would have said that, oh, well, V, oops, let's get rid of this highlighter nonsense. I would have said that the velocity squared over r is equal to, and I've already kind of canceled g's, or m's, we have g cosine of theta over sine of theta. Well, I'm going to multiply this side by sine of theta and divide it by cosine of theta. And so what that does is that gets rid of the cosine, it gets rid of the cosine here, and it gets rid of the sine here. But what I've done on this right side of my equation, I have to do on the left side as well. So now I'll multiply this by sine of theta and divide it by cosine of theta. And we'll end up having this essentially sine theta over cosine of theta, but I'm just going to rewrite this as tangent. Tangent of theta times v squared over r gives me g. But again, we want the angle alone, so really I'm just now working towards getting this little theta alone. And so I'll just go ahead and I'll do a similar tactic. I'm just going to multiply this side by r and divide it by v squared. And I'm doing that because I'm going to do the same thing on this left side. I'm going to times this by r divided by v squared. And we can see here that the r's cancel. We can see that the v squareds cancel. And so kind of simplifying this down now, I just have that tangent is equal to, and we have g r over the velocity squared. Now the last step to get this angle itself alone is take an inverse tangent. And the reason I say that is because tangent inverse, or the inverse tangent of tangent, this just like gets rid of each other. It's like if you had 2/3 and then you multiply it by 3/2, they just are the opposite. And so these cancel out, you end up just getting 1, and you just kind of get the thing alone. And so this is going to work almost the exact same. We're doing this on the left side. We're going to do it on the right side. Take the inverse tangent of now g times r over the velocity squared. And again, we see that inverse tangent and tangent kill each other off. So really all that's left on this, well, left side is just the angle. So the angle is just equal to all of this here. And so that's exactly what I have right here. And then I just have I've plugged in because we were told that the radius is this 0.5 meters. Well, we know what gravity is. We were told how fast it's going. We're going to make sure we square the thing, and we're just going to get this angle, really. Now, I went and I rounded it to 2 significant figures, and actually there should be a period here, or a decimal here, to actually give that 2 significant figures, because 3.7 has 2, and 9.8 has 2, so it should have 2. And I hope that makes sense for this number 7. Thank you.